Our next speaker is Dr. Brian Looney. Brian received his PhD in environmental engineering from the University of Minnesota in '84. And he is an environmental engineer in the Savannah River National Lab and adjunct professor in the environmental engineering and earth sciences department at Clemson. Over the past 35 years, Brian has developed and deployed a wide range of environmental characterization and cleanup technologies, and has supported DOE offices of environmental management and legacy management across the country. With that, Brian is going to talk to us about natural attenuation.
Thank you, Ming. So for the past 20 years or so, we have participated and collaborated with other laboratories, with universities, with industry in a technical assistance program. And in that program, we go to various sites and we try to address what are considered difficult problems for the site. Oftentimes when you go in, it's a problem they've been dealing with for a good little while. And so we go in and we basically perform a triage process. And that triage basically tries to quickly look at the situation and see if something is being missed, to see if there's some creative or scientific idea that would really help them, to kind of put them over the edge and be of assistance to them. So what I'm going to talk about today is really some lessons learned from that. And in a lot of ways, what this does is it puts some meat on the bones of what Mike talked about earlier. So he went through kind of a general process, and I'll give some examples where we put a little bit of meat on some of those bones where we go in. It's a little bit easier to see when you look at a specific example as opposed to kind of just the general flow chart. And in particular today, I'm going to talk about a class of remediation strategy that we call enhanced attenuation. And we'll define that in just a second and kind of go into what that means. But by way of background, the kinds of sites that the Department of Energy deals with are fairly diverse. We have liquid sites like pits, ponds, and lagoons. We have facilities, buildings, silos, uranium mines, mills, and tailing sites. We have solid waste, we have cylinders. So basically the theme of today's talk is kind of diverse stewardship challenges require diverse solutions. And they need to be customized and they need to be aimed at specific opportunities that the site provides to us. Let me provide a few definitions up front since we're building this around the idea of attenuation-based remedies. The official EPA definition is for monitored natural attenuation, and that is a cleanup strategy that relies on physical, chemical, and biological processes that act without human intervention to reduce mass, toxicity, mobility, volume, or concentration of contaminants. So that's the official EPA definition of monitored natural attenuation. We'll get into in just a minute, there's some challenges in getting exactly to that point. So we worked with the ITRC and we developed an idea called enhanced attenuation. And it's basically a bridge between our active treatments and monitored natural attenuation, have had significant success in kind of moving these sites from more active treatments to more passive treatments over time. Definition of an enhanced attenuation, this is from the ITRC Tech-RA guidance document. Any type of intervention implemented in a source plume system that sustainably increase the magnitude of attenuation by natural processes. So this would be basically an action that you take, an engineering action that you take that increases the attenuation capacity of the system. So we had diverse stewardship challenges required diverse solutions. We also have diverse contaminants. So we have things like organic contaminants, and the preference, the regulatory preference of those is degradation and mass removal. Then we have metals and radionuclides. Well, they're not degrading and going away, and so typically attenuation-based remedies for metals and radionuclides are built around the idea of reducing mobility and or toxicity. And so what you have is you have diverse sites, and you have diverse contaminants, you have diverse geochemistry, you have diverse hydrology, you have diverse meteorology, and all of the other site boundary conditions at these various sites. So it becomes quickly easy, being at a national laboratory, if we wanted to do this in a very basic science way, we would sit down and make a list of all the stuff we don't know. And I could make that list for days. I could sit down for days and write down things I don't know. And so what you get is you go to the scientific literature and you have triple layers, double layers, ZAFs and ZANEs, zeta potentials, Mossbauer, frayed edge clays, geobacter. You have all these things in the literature. And if you go into a site in kind of an unconstrained way, you can quickly get yourself into kind of a paralysis by not knowing what's going to be important and having some way to structure and to prioritize. So what we find when we do these little triage exercise is we want to focus the science on the specific problem, the specific site, and the specific thing that's viewed as the failure. What was the failure? And then when you apply science, that's how you put science to work, because what we find is that at most sites, if we start with what we know, which is typically the nature of the source, something about the contaminant distribution, the biogeochemical conditions in the plume, the biogeochemical conditions in the region, the geology, the hydrology, the general contaminant chemistry, where water comes in the system, where water goes out of the system. You often know 80 or 90% of what you need to know. Well, what that does is it constrains that last 10 or 20% we now can apply the science to and try to figure out what a potential solution is. I'll give some specific examples in just a minute. But the way we do this then is we use what we call frameworks. So we take this knowledge and we take Mike's site-specific conceptual model, and we kind of lay that out. And then around there we put this balloon of different ologies, so hydrology, geochemistry, etc. And what we find is that the plumes position themselves in space, and so you need to understand where they are now. You need to understand where they are in plan view. You need to understand where they are in 3 dimensions. And then you need to understand what's happening to them in the past and in the future. So you have the temporal framework, the spatial framework, the geochemical framework, the hydrology framework, and then other. This would be ecology, this would be the stakeholders, this would be the risk assessment, and all of the other things that can be brought in. So if we go back to the original EPA description of natural attenuation, this is a figure that I actually pulled out of an EPA support document. And what you see is that plumes over time have different stages. There's a period where you have a source zone, and then they expand. And then when the plume status is really controlled by the mass flux and the mass balance, when the attenuation mechanisms in the plume footprint are approximately equal to the flux from the source, the plume will stabilize. And then over time, as the source decays, you'll basically get a shrinking plume and then ultimately an exhausted plume. It's a little more complicated than this, but basically this is the kind of EPA description that was put into the basis for natural attenuation. So the requirements for monitor natural attenuation is that you have done source remediation to the extent practicable or practical. We saw that in Rob's talk earlier. The plume poses minimal risk, and remediation goals will be met in a reasonable time frame. Notice that they didn't put an exact number of years on there. And so the colloquial definition of reasonable is that the attenuation time frame is similar to the active treatment time frame, that they're in that same kind of order of magnitude ballpark. That the plume is stable or collapsing. You can't do natural attenuation if the plume is expanding. You can do monitoring to ensure that attenuation mechanisms are in place and that they're sustainable. So we're going back to Rob's description of what he looks at in the five-year review. And then you have to identify triggers that implement contingency plans as needed. So if things don't go the way you expect, you have to have predefined what your action is going to be. It may be that I just increase the frequency of monitoring. It can be all kinds of things, but you have to have that defined. So that's kind of the EPA description of monitor natural attenuation. If we look at it more from a technical perspective and a mass balance, what you can see is you have this source, and then the width of these arrows is really supposed to be proportional to flux. So you have a flux coming off the source, and then as the contaminant moves through the plume, you have a progressive decrease in the mass flux, and it's due to chemical, biological, and physical processes. These things that EPA defined in their definition of natural attenuation. Chemical processes can be sorption or abiotic degradation, for example, interaction with reduced iron in mineral phases. You can have biological attenuation, you can have aerobic or anaerobic. You can have dispersion, diffusion, advection. These are pretty weak attenuation mechanisms and not kind of, typically we wouldn't use as a primary. Then we get through and we basically have a flux to a compliance point or a human or a receptor or an ecosystem. And what you can see is that this width of this arrow is wider than the target. And that basically means that we have to do something else. This is typically what we see. And then we can do pump and treat, active remediation, or we can do something else. So the idea of enhanced attenuation is to think about, are there things we can do that actually reduce the width of these arrows? And now all of a sudden, when you think about it this way, you have all kinds of control knobs to turn. You have all kinds of scientific opportunities available to you. So you can just reduce the amount of water flowing through the source. That reduces the flux from the source. You can increase sorption or abiotic degradation, for example, by putting a reductant in that reduces some of the iron to reduced iron. You can add electron donor or electron acceptor to increase biological attenuation. So basically what you do now is you peel off more of the contaminant, and by the time you get to your compliance point, you've shown that you meet your regulatory goal. So that's the simple idea behind enhanced attenuation is it's now with human intervention. You're using an engineering activity, you're using human intervention, and you're transitioning the site into a sustainable natural attenuation mode. The reason this became necessary is as we went around the country and here at Savannah River site, there was this kind of, for those of you who are Star Trek fans, the Kobayashi Maru, the no-win situation. So we would start a pump and treat system. And in order to monitor natural attenuation, you had to have 5 years of data that was representative of what would happen without the pump and treat system being on. And you couldn't turn off your pump and treat system, so you couldn't get the data that you needed to do monitored natural attenuation. And we had a boss at the time, Bob Aylward, who just retired yesterday. And Bob used to say, when you work with regulators, you need to give to get. And so we thought that was a really good thing. And so what are you doing? You go to the regulator and you say, you're not saying, I want to turn off my pump and treat system and then just do nothing for 5 years. You're saying, I'm going to do these actions. It's going to increase the attenuation capacity of the system. And then I want to do that and watch it. Now you're giving something and not just turning something off. So here's just a picture. And you can see this kind of thing happens at every site. This is a mom and pop gas station. This would be a large DOE site. It's a complex plume. This would be a campsite where you have a fire pit. Okay, you have kind of a source zone. The impact expands off of that. You have this impacted zone, and then you have a zone that's further out that is transitioning more to a natural condition. And what we do in our tech assistances is we basically have a chart that matches up technologies to the different zones. And one of the first things we did is we made this picture in about 1987. We went to the National Research Council and they said, how do you do remediation at Savannah River? Why are you so successful? And basically we put these pictures together to try to explain what we do. What we do is we try to divide the plume into these zones, and then we try to define what our behavior is going to be in each of these zones. And in the red zone, it's a source zone, so you use aggressive technologies, you use strong chemicals, you use removal actions. When you get into the green zone, you do more traditional things. You can do pump and treat, you can do bioremediation, you can do things like that. So what we do is we basically have a map that maps different technologies to the different zones. Well, now when you're working with your regulators, it becomes a very positive experience because now you can basically argue over what the edges of the zones are. But then once you finish that conversation, everyone knows how you're going to behave once you're inside those zones. And here's just a map. What you can see is in the red zone, you have excavation, some in situ bio, in situ chemical destruction, thermally enhanced removal. In the green zone, you have pump and treat, recirculation wells, in situ bio. And then you get out into these enhanced attenuations, and we'll define what that is in just a second. So we worked with ITRC, and the idea for enhanced attenuation is let's figure out a way to make a bridge between active remediation and monitored natural attenuation. And so the idea was it's not just a one-way bridge, it can be a two-way bridge. So this is contingencies. So the bridge can go back and forth. And it was developed by ITRC, state regulators, EPA, DOE scientists from various laboratories. And again, being ITRC, it's a flow chart. But it's a really interesting flow chart, and I'm not going to go through the details, but I'll just point at the different zones. So here's all the different data that's coming into our system. And what you do is you start with the plume at the top, and you do an evaluation of plume stability. So you try to figure out whether your plume is stable, shrinking, or expanding. So you just kind of a snapshot of that. And then you go down, and these questions are the exact questions that EPA asks in the Monitored Natural Attenuation guidance document. So, are the risks acceptable? Is the plume stable or shrinking? Are the conditions sustainable? Is the remediation time frame acceptable? Well, you basically ask all those questions, and the answers can be yes or no. But now you actually define what are the one or two things that keep you from doing natural attenuation, because you now have looked at those questions. And if the answer to any or multiple of those questions is no, it sends you over to a new area, which is called enhanced attenuation. If the answer is yes, you actually can do monitored natural attenuation. If the answer is no to anything, it sends you over here, and you basically evaluate technologies that would allow you to modify the site to address whatever sent you over there. So if the time frame isn't acceptable, is there something we can do to speed things up? And can we speed it up in a sustainable way? Okay, so those are the ways you ask that question. If sustainable enhancements are viable, then you implement and monitor, and then you go kind of back through the system. If sustainable enhancements are not viable, it's not a problem. You just go back and you continue to pump and treat. Okay, so this is not something that we get upset about or whatever. It's just a process by which we can think about the site. So I'm going to do 3 quick case studies. I'm going to talk about Mound Operable Unit 1. It's contaminated groundwater from a former landfill. And the technology we use there is actually the same technology that Rob showed the site of T-area. It's the exact same technology we used at T-area earlier. But this is a more recent example. I'm going to talk briefly about the F-area groundwater at Savannah River site. So it's radioactively contaminated groundwater from former seepage basins. And I'm going to talk about something we've done very recently at Tuba City, which is a site that is a uranium mill and tailing site. If I look at Mound OU1 groundwater, basically we have these check boxes up here. So they did a source removal action, so source removal is complete, check, right? We had an operating groundwater pump and treat system, check, okay, we're all good. Well, that operating pump and treat system had been going for about 15 years or so, and the plume had stabilized, and it kind of hadn't changed for 10 years or so. So basically what happened was they turned it on, they got some initial removal, the mass removal kind of reached a plateau, and the plume footprint and shape really didn't change much over time. Now, what we want to do is transition the groundwater remedy to an enhanced attenuation, and we use the same technology as T-area, and we call it structured geochemical zones. And what you try to do is you try to take advantage of the strengths of different types of microorganisms, and what you see is that anaerobic consortia are really good at degrading compounds that have fully chlorinated, so TCE and PCE, and then aerobic processes are really good at degrading things that have few chlorines, DCE and vinyl chloride. So one of the problems with a regular design for a bioremediation is in order to get DCE and vinyl chloride to go anaerobically, you have to push it so deeply anaerobic that it has adverse collateral impacts on the aquifer. So you have to make a large area deeply anaerobic, and this particular aquifer is a sole source aquifer that's an important resource to the city and the community. So what we wanted to do was keep this as compact as possible and yet still meet our goals. Well, the way you do that is you actually make a sequence of anaerobic and aerobic zones so the water flows through anaerobic zone, aerobic zone, anaerobic zone, aerobic zone, and each then does its strength. That's the idea. That's the design basis. The anaerobic zones stimulate the parent. The aerobic zones stimulate the daughter degradation. And then what we see is lots of other things. So the source zone, you're generating reduced compounds, methane, other things like that. The methane coming off of there into the aerobic zone stimulates methanotrophs. Methanotrophs are a class of organism that will also continue to degrade TCE and rapidly degrade DCE and vinyl chloride. So that's really the technical basis of it. So what we did is we went out and we injected pure vegetable oil, neat oil, into the Veda zone beneath the former landfill. That goes down and it spreads out on the water table. So now any residual source coming down through the water table has to go through that oil and kind of reduced zone. Then as we went down the core of the plume, we would have an anaerobic zone, an aerobic zone, an anaerobic zone, and an aerobic zone. And that's basically how we designed it. Well, here's the first couple of years of data. This is T0 when we did the injection. You can see we had a pretty good plume. This footprint, as I said, had been stable for maybe 15 years. Hadn't really changed. This is after 3 years, and it's even less now. So basically, this is after 3 years. We're at year 4 now. And you can see that we had a pretty big impact in the first 3 years. When we designed this, we estimated all wells would be at MCL within 12 years. We're down to the point now where there's only 2 wells that are above MCL. So we're pretty confident at 4 years. So we're pretty confident that we're actually going to meet MCL at all wells in 12 years. So basically, we accelerated progress toward the remedial objectives. We reduced costs. Cost savings here is in the order of $5 million or so. We had a core team concept here like we have at some of the other DOE sites. So DOE, the regulators, both state and federal, they meet and they actually look at the performance of this on a regular basis and then make decisions about whether we met the performance criteria and whether we need to trigger a contingency. So basically, the questions that the core team is going to look at the end of year 4, which is right now, has the EA remedy effectively transitioned the site into M&A? And is the attenuation likely to continue to be effective, timely, and sustainable? So those are the questions that are being answered right now. And if the answers are yes, this will then officially transition into a monitored natural attenuation. So that's kind of one case study that we did. This is a busy slide, but I just want to quickly go through it. This is F area, and I'm not sure if you'll see it on the tour, but basically F area was a series of seepage basins that received acidic, primarily acidic wastewater and various contaminants, so basically strontium, iodine, tritium, technetium, other things like that. And what we did is we closed the basins and capped them and worked with the regulators, and the regulators wanted us to put a pump and treat system in. So we put a pump and treat system in, we treated, and then, of course, we weren't taking tritium out. So the fix was going to be, we'll pump tritium up the hill and we'll re-inject it, and then we'll give it more time to decay. And, of course, that worked really well for the first few years, but nature doesn't take kindly to things like that. And so rainfall's still coming in, and so basically after about 4 or 5 years, we had reached a new steady state where the amount of tritium coming out was about the same as when we started. So nature is very unforgiving. Water comes in, water goes out, and you can't set up a perpetual motion machine within there. So what we did was we did some research, and we found out that most all of the contaminants could be geochemically immobilized, and we built a funnel and gate system. And the basis of that funnel and gate system was some detailed geology, and what we saw was that there was some structure on the confining zone. And on that confining zone, the highest concentration of the plume was down in those trough features. And so what was done was we put in walls that block those troughs, and that basically partially stagnated that water. Now it has to move and slowly come up and around and go through the gates. Well, now having all the water in the gates is an opportunity that we can add chemicals for treatment. So we put in a funnel and gate system where we put in a treatment material and basically reduce the contaminants and immobilize them in the gate area. That worked really well. And even tritium, because it slowed down as it gets to here and has to come up through the gate, we had about a 70% reduction in tritium, even though the chemicals we're putting in don't really do anything for tritium. Now, interestingly, the chemicals we're putting in don't do anything for iodine either. And so basically iodine was going through. And this is a good example of the state and DOE working together, because they basically said, let's do this, get back with us on what we're going to do on iodine. And we had a person in the lab work, and we developed an innovative technology where we put in silver chloride, and the silver precipitates the iodine, and so we can just add that into the gate, and now we have a solution that ties a bow around that part of the problem. We have future regulatory commitments to try to meet standards down gradient of the wall out in the wetland area. But once again, it's this phased approach. You bite off something that you can be successful at, you develop an innovative technology, you put it in place, you take actions to make sure it's working, and then you move on to the next regulatory objective. Now, this is a really interesting example at Tuba City. So up on top of the hill is the tailings pile in the old mill, and what we have is a 900-foot thick aquifer, and all the contamination is really in this very upper part of the aquifer zone. Now, this is a case of kind of thinking about stakeholders. So the stakeholders, the Hopi and the Navajo, who adjoin this land, this is Moenkopi Wash down here, and at meeting after meeting, the Hopi and the Navajo said, the things that are most important to us is that DOE contaminants don't get into Moenkopi Wash, and that if it's possible, we need to have water available, and you've basically contaminated this water and taken it out of being available. So this is a modeling discussion. So in the modeling, what we figured out was that with data from Jody Waugh and others, is that most of the contamination was actually being taken out by evapotranspiration. But that's not a traditional boundary condition that you can put in mod flow. And so kind of the path of least resistance is, well, we just won't put that in. Then we'll go to the meeting with the Navajo and the Hopi and we'll say, it's all good. It's not going to reach Moenkopi Wash for 600 years, and it's only going to be half of drinking water standards. Do you think they were happy? They were not happy. And not only that, you basically have this water that's contaminated. But when you start thinking about this, if you put the ET boundary condition in and you take off the pressure of this, if you basically say nature's taking care of it and it's not going to get into Moenkopi Wash, it gives you all kinds of scope for imagination. So for example, we can put horizontal wells in here, and we can collect water up gradient that's clean, and we can give it to the Hopi and Navajo to grow crops. It can lower the water level at the site. It can strand the contamination in the Veda zone. We can lock things down. So there's all kinds of things that when you do this, you can come up with different ideas. So here's just a picture of that idea of taking up gradient water, lowering the water level, and then this becomes available water, and you have good confidence that you're not going to impact Moenkopi Wash. So in conclusion, enhanced attenuation remedies represent a strategy to address the diversity of DOE challenges. It often is something that's done in sequence after you've done some source removal and some other type of activity. They support the formulation of alternative end states. They foster creative options for long-term monitoring. They need to consider, and this is really important, be consistent with the regional biology, the regional chemistry, the regional hydrology, because those are the things. So for example, if you do an anaerobic process in an aquifer that's going to eventually be aerobic, you're fighting against nature. So if you can come up with a clever geochemical idea that's aerobic, you now are working with nature as you move forward. So these are just the simple principles that we use when we do these technical assistances. So that's all I have. Thanks.